resilience is one of those words and terms that might have been very overused, and everybody's rolling their eyes over resilience when it comes to security, especially ICS. So here's my quick take on it and why I think it is one of the most important aspects of everything we do. And as an asterisk to my take, yes, I did put in some years of work in automotive for business continuity. But being an incident responder, we follow the mantra of 2 is 1, 1 is none. So basically resilience comes under everything that we do as incident responders, because we see everything break out there in the field when we're engaging. But also looking at my past year, that other level of resilience that is even more important to my job and basically keeping me functioning these days is having the mindset of knowing enough to get through things no matter what. And these are my 2 takes. So I'm really looking forward, Johannes, to your takes on engineering for resilience. To give a little bit of background on Johannes, he's a senior advisor for ICS Cybersecurity at Royal HaskoningDHV. And I hope I didn't fully butcher that name. My family comes from Denmark originally, like 300 years ago, and was kicked out of the country for butchering the language. No, different reasons. Your focus, Johannes, these days is exactly on cyber resilience by design and what is good enough and how do we architect this into our designs. With that, looking forward to your take on resilience. The floor is yours.
Thank you, Kai. I expect you can hear me now. Now I hope that I can control the screen as well. Yes. So that's the title of my talk, Engineering for Resilience. There's 2 important words in the title of the talk. On the one hand, engineering, which is a methodology that's being used when you're designing complex systems. And on the other hand, resilience, meaning knowing what to do when you're compromised, knowing how to limit the impact of a compromise. But before we go into the content of the talk, let me first introduce myself. I studied electrotechnical engineering way back, and I worked for KPN, a telecoms company, for 29 years. 18 years of those I was an IT project manager, so I have an IT background as well. And since 2015, I'm involved in cybersecurity in industrial automation. In the first few years, I worked at a project for the Dutch Highways Agency, where we went to all the sites and investigated security and safety. And since 2017, I joined Royal HaskoningDHV, an engineering company. And I have a few cyber-related certifications. In 2015, I did the ICS 14 with Justin Searle and Eric Cole, and a couple of months later, I got the certification. And last year, I'm proud to say I also got the CISP certification, and also know a little bit about 62443. So that's the basis. Now, the company I'm working for, International Engineering and Project Management Consultancy Company. So we employ consultants, engineers, project managers, etc. We have about 6,000 colleagues over 140 countries. We are one of the top 50 engineering companies worldwide, 650 million turnover in 2019, and we lead in sustainability and innovation. And we have global expertise. So we exist now for almost 140 years. So this year, back in October, is celebrating that 140 years, and throughout the years, we are publishing stories from our lifetime. All the blue countries is where we have local presence. So you can see we're really a global company. And what we do is we work in these environments: aviation, buildings, industry, infrastructure, helping our clients with the design of new structures. And since last year, we also have a digital business line. That's that. Let's go into engineering for resilience. Now let's look at a complex system. And I think everyone will agree that an elephant, a living organism, is quite a complex system. Although on the outside, it's fairly simple. It needs some input, which is food. It processes that input. We call that digestion. and it produces wanted output, labor sometimes, and it may also produce unwanted output. But when it gets sick from wrong input, we can use that unwanted output to diagnose the cause of the illness. And when we look at a complex infrastructure system, again, it's similar. It needs input, although this time we're talking about commands, clicks, and sensor data. It processes that input, we call that computing, and then something happens. It activates an actuator. For instance, it opens a bridge. And it also produces, in some ways, unwanted output. Log data has been ignored for far too long. And it too can get sick if you give it the wrong input, and wrong input being erroneous commands, viruses, malware coming in, ransomware coming in, crypto mining even coming in. All that has happened in the industry. And initial diagnosis can sometimes be done from the log data. Now, look at an example of a tunnel system, which is more complex than quite a few people in the world would think. There's quite a lot of drivers that see a tunnel as a hole in the ground with lighting, and they can drive through it. But there's more to it than meets the eye. There's a lot of stuff that's visible to drivers, and there's a lot of stuff that's invisible to drivers. So to give some examples, drivers will see traffic lights, traffic barriers, and traffic management indicators. They will see maybe the height measurement that's trying to prevent lorries that are too high to enter the tunnel and damage it. Then there's ventilation systems, which is sometimes difficult to see, but you can still see them. The illumination already mentioned, that is clearly visible. And then there's cameras in the tunnels, but they are quite well hidden. There's a broadcast installation if you're driving through a tunnel and your radio keeps on playing, or when something's happening and the operators send messages. Then there's escape doors, and believe it or not, I've spoken to people that have driven through tunnels and have never seen those escape doors that are there every 250 meters. And there's aid stations for when something goes awry in the tunnel and you need to extinguish a fire. But there's also a lot of stuff that drivers can't even see. If something goes wrong in the tunnel, it needs to be detected. And if there's a fire in the tunnel, then everybody needs to be able to escape. And it would be handy if that escape route is safe and not filled with smoke, so you have an overpressure system in the escape route. And there's drainage systems to get fluids out of the tunnel. There's air quality measurement. There's a firefighting system. There's a control system. There's an alarm system on the service building. There's climate control for that service building, because that's usually where all the computers are hidden. And there's much more that I think this pretty much gives the picture of how complex a tunnel system is. Now, let's talk about resilience in the life cycle of assets, because I think it all starts at the beginning, and the beginning is when you're formulating your requirements. And then you have to take it through the design phase, implementation, operation, and evaluation phases. So if you want to reach security by design, then you need to think about security right at the start, right when you're formulating your requirements. You have to have those cybersecurity requirements up front and integrate those into your complete set of requirements. You have to do cybersecurity in your validation and verification phase, as Dieter also talked about. You have to do continuous monitoring and operation. I've talked to people who say, well, cybersecurity, aren't we now done with that? No, you're never done with cybersecurity. It's a continuous point of attention. And the basis of cybersecurity, one of the foundational items, in my view, is asset management. You need to know what you have. It has been said before yesterday. You can't defend what you don't know that you have. So you have to know how your network is built up. You have to do your risk assessments. You have to know your risks and your mitigation measures. And you have to do scenario and simulation modeling, know what could happen if something goes wrong. Now, the threats, you can control to a certain level the threats that you might be you might encounter. So you have to identify your assets and your processes, And we call that the system identification. And you have to conduct risk assessments. You start those at a high level of the system as a whole, but then when you go into the engineering and systems engineering methodology, you break the system as a whole up into subsystems, so you can do your risk assessments for the subsystems as well. And when you've done your risk assessments, you have to know your risk tolerance, because that will tell you whether you have to do to take some mitigation measures. The risk tolerance and the risks you've identified together give you which risks need to be mitigated. And that mitigation, you need measures, you need to formulate them, you need to implement them. And when you've implemented them, you need to assess the new situation in order to see whether you were successful enough or additional measures are needed. Now, what kind of threats do we have in the infrastructure? This is a little bit of an overview. I'm not going to read out all those things, but in my view, if you're working in infrastructure or in road infrastructure, in my case, such as tunnels, you have to be aware that the guys that would be targeting you are the cyber criminals and the nation states. Those might be interested in those kind of systems, and they might lead to physical damage, physical harm. So the traditional approach of designing and building such a system, we design a new complex system, we build and test it, and we put it into production, and usually for 10 to 30 years or 50 years even, as I heard in the talk yesterday where somebody wanted a contract for 50 years. And don't change it as long as nothing breaks. That's been the adagio for quite a few years. If it ain't broke, don't fix it. So we just wait for something to go wrong, and when it goes wrong, we have to find out what to do. And when we have found that out, we can remediate the effects of something going wrong. A little bit less traditional approach, in my view, is we design a new complex system again, and we build and test it, but then we perform a penetration test of that system. So we look at the parameters, and we can secure the boundaries of the system. So maybe nobody comes in. And we also write an incident response plan, and even better, we are going to test the incident response plan. But again, we put the system into production for that same life cycle, and we don't change it as long as nothing breaks. We monitor the log data, and again, another item in many infrastructure environments. And as I said, we practice the incident response plan regularly, so we know what to do. We know which people to contact when something goes wrong. And again, we wait for something abnormal to appear in the log data, and then we put the plan into action. Now, what I would like to see is the resilience by design approach. So you design your complex system with security in mind from the get-go, and you perform a high-level risk analysis of the entire system. We decide on the risk appetites, and then you decide on your security level target. That's a term from IEC 62443 for those who are familiar with it. And you incorporate those mitigating measures into the design. Some of those measures you can only incorporate into the design and are very difficult to incorporate afterwards. So, something like input validation is something that you need to think of when you're designing that software. We build and security test that system, and that's much more than penetration testing, because penetration testing looks at the system from the outside, and security testing looks at the system from the inside, and for instance also looks at input validation stuff. Does something go wrong when I give a system input that it doesn't expect? We can, of course, do the penetration test, and we put it into production. But as we have thought about security from the get-go, we've also built into the design the possibility to have it updated during its life cycle. So the don't fix it when it's not broke adagio is out the window. We now keep it up to date. We apply patches when necessary. Not each and every patch that comes by might be necessary, but if need be, you can update. And we monitor not only the log data, but also the network traffic, because that gives you much more information. And we expect something to go wrong. We expect something to appear in either the network traffic or the log data. And again, that incident response plan that's put into action when something goes wrong. Two models from IEC that I find very illustrative. We have owners. They have put value in assets, and they want to have an acceptable level of risk for those assets. On the other hand, we have threat agents, and they want to abuse or damage those assets for some reason. So they give rise to threats that increase the level of risk to those assets. So the owners, they need to have countermeasures to reduce that level of risk again to reach that acceptable level. Now, another model that helps is the threat risk versus information security assurance model. We have again the owners, the threat agents, and the assets. So the threat agents, they give rise to threats, and they use vulnerabilities and weaknesses. So we require countermeasures to minimize or reduce risk to the acceptable level. On the other hand, the owners, this is the threat risk assessment field. Now, the owners, they require confidence in those countermeasures, and they get that through assurance. And for that, they need assurance techniques to produce that assurance, and the evaluation gives evidence of that assurance. And that's your information security assurance field. Now, as I said, we're going to do risk analyses, and we have to identify the system under consideration. And at first, that's the system as a whole, and later that can be subsystems. So we have to identify the main components of the system, describe their functional roles, interfaces, and context. We use a risk methodology, and the standard doesn't prescribe one. It just says do a risk assessment. And we have to identify those threats. And therefore, for that, we can use threat modeling, attack trees, etc. And for each threat, we have to formulate risks. That can be multiple risks for a threat. And I'll show a couple of examples of that later on. And we have to estimate the likelihood of occurrence of an attack as well as the likelihood of success. And that gives the probability of the risk. And we have to estimate the impact of the occurrence of the risk. And then you can do two things. When you can compute everything, you can do it quantitatively, but it's very usual to do it qualitatively. So we use heat maps. Now let's talk about those heat maps using an example. You see a house here which has an obvious weakness. There's a hole in the roof. So yeah, there's a weakness. And the threat is that the interior gets wet. The impact is that you get interior damages. Now, here's a heat map for the probability. And one of the things I'd like to stress, if you use heat maps, you have to define those terms. Low, medium, and high, they have to have a definition because they might mean something completely different in a different organization. And please don't put values there like 1, 2, and 3 and then start multiplying those values and saying, well, then if it's a high likelihood of occurrence and a high likelihood of success, then we reach the very high probability, which is 9. That is like multiplying apples with pears and saying that you're getting a strawberry out of it. Now, the impact analysis is back to our house with the hole in the roof. There's the weakness again and the threat. Now, there's a likelihood of occurrence. In the house in the desert, then it doesn't rain very often in a desert, so the likelihood is low. If it's in Holland, it rains quite often, so the likelihood is high. So when it rains, the hole will leak. The likelihood of success is still high. Now the probability, if you look at the heat map, then in the desert, the probability is medium because it doesn't rain very often. And in the Netherlands, the probability is very high because it rains very frequently and very heavily. And the impact then is interior damages. So we get to the next heat map where we go from probability to impact. And again, the advantage of using heat maps like these is this one is diagonal, but you can decide, for instance, that for a catastrophic disturbance, no matter what the probability is, it's always catastrophic risk. So it doesn't need to have this diagonal organization. And again, define those levels very clearly. Again, now the same house again with the hole in the roof, impact analysis. Now the probability was medium when it's in the desert. But if the house just contains old furniture, then the impact is very low because that old furniture, well, you don't really care about it when it gets wet. But if there's, let's say you have a low level of risk. Now, if the house contains a valuable collection, then the impact is very high, and I think there might be more things you'd want to do to a house that contains such a collection. So the risk level is catastrophic. And unless you decide to accept a catastrophic risk, I expect you want to take a mitigating measure, for instance, fix the hole in the roof. Now, a more realistic threat in an industrial environment is that unauthorized people gain access to a SCADA system. And there's two possible threat vectors that I'd like to talk about. They gain physical access, or they can gain logical access to that SCADA system. And from those threat vectors, you can formulate risks. For instance, if they get physical access, if they obtain the key to the technical room, then they can get physical to the system and they can shut it down, for instance. Or when they use such social engineering to gain access, for instance, tailgating, or they go in and need to say they need to repair something, they can get access to it. Or they can just plain old break into the room. Now, logical access, you can obtain login credentials one way or another, for instance, through phishing, and gain logical access to the system. And then we've already seen earlier today what people can do then. You can also, if there's an existing connection to the outside world, and it was mentioned in the previous talk as well, that might also give you access to the system. And even when it's protected remote access, you can break the protection. You could break the protection and get in. If those risks, you can build a likelihood matrix. For each risk, you have to estimate the likelihood of occurrence, the likelihood of success, and from the heat map, the first heat map I showed, you get the probability. This is from a risk assessment I did with more than the six risks I showed earlier. You can plot those on the heat map, and then you get an idea of where you're at with your risk level when you're in an unmitigated situation, and which is pretty dangerous. Now, then what? Based on that high-level risk analysis, we define mitigating measures, and we have to realize that those mitigating measures might partly mitigate multiple risks, and some risks may need multiple measures in order to be reduced to that acceptable level. And those measures, they can be organizational, they can be procedural, they can be technical. So that needs to be a balance between those three categories. In my view, if you only do technical, you almost might as well not do anything, because if you don't educate the people, if you don't have the right procedures in place, it's not going to work. And so you have to map those risks and measures to those risks in order to know the relationships. When you have to make choices because the budget doesn't allow for all the measures to be taken, then you have to know which measures have the highest impact and need to be done first, and which measures might be postponed until a later date because they have less impact on less risks. And you have also to map those measures to the subsystems in your system breakdown structure in order to know what the effect is if you can't implement some of those measures, and you have to maybe put in compensating controls. And that's where you go for the detailed risk analysis on the subsystem level. Now, as I said, there's organizational measures. You need to identify the responsibilities. You need to look at the contracts. You need to secure your supply chain. There's configuration management. There's key management. Procedures. You have to think about information security. And again, referring to an earlier talk, if someone can easily find the documentation for your ICS environment, then they can take that home and study it before they launch that attack. There's security awareness. You need to do something about that, and that's more than just once giving a presentation. You need to repeat that. You need to maybe do more stuff than that. There's also secure software development, because security is in the software as well. It's not just the physical security. It's not just the networks. If you look at the OWASP top 10, and people say, oh, OWASP, that's web application. Yes, true, but a number of those techniques can also be used against industrial software. So you have to look which of those top 10 threats are applicable to my industrial environment, industrial software as well. Change management, reporting, business continuity has been mentioned, incident response has been mentioned, and then you get into the technical stuff that you have to do. And you have to do most of those in balance with what the organization thinks is acceptable. So here's an example of a risk matrix. The probability I've shown earlier, that you get the impact, and then from the second heat map that I showed, you get the risk that the level of risk that you're running, which is pretty darn catastrophic, 3 times, and high 3 times. So you probably need to do something about this. Now, if you do something about it, then you still can think about what if I take a set of measures, or maybe even take another set of measures. So and then you can compare the 2 results, which is what I've done here. Put in a number of measures, and maybe put in a number of extra measures to get the level of risk further down. Now here's the unmitigated heat map again, and if you put in the first set of measures, then you see all the risks go down and left, and then we get the level 2 set of measures. It goes down even further. So the key takeaways from this are: feed your complex system well. Prepare, for instance, in your design. Use well-defined risk management, even if you're doing it qualitatively. Define the terms that you use so that everybody knows what you're meaning. Implement those mitigating measures in the design in order to reach that acceptable risk level. And from the design, you have to do the testing. Even during design phase, you have to review those designs, whether those measures are really taking into account in the design. And you have to balance your organizational, procedural, and technical measures. So that's my presentation.
Thank you so much, Johannes. Especially those takeaways. I think everybody should really take away from this also, pardon the pun, but one question I have for you is, when I look a few years back, especially here in Europe, a lot of the conversations I had, especially with top executive level in the manufacturing and automotive environments I was working in, usually were kind of overshadowed by sort of fatalism, especially when the discussion went exactly around what you mentioned, highly organized crime and nation state types of attacks. It was along the lines of what might have been also underlined by what we saw with NotPetya, and then Zurich Re not paying out the insurance premium. It's like, we can't deal with this stuff anyway. So why should we even look into the high risk or catastrophic area of that CRAM-like approach that was on your matrices? So what is your take on usually trying to open up that discussion that it is your job, folks, to deal with that?
Yes, because I think there's a couple of things that can be said about that. You mentioned NotPetya. I mean, how many companies can survive a damage of 600 million euros and still be in business? So not thinking about those high-level risks might endanger the survival of your company. And I think that top-level executives are there for what are, among other reasons, make the company survive. And yes, if the top-level criminals and the nation-state actors, they are the top of the line, and they have the most resources, and they can wait. They have a lot of time on their hands. But then again, if you make your environment harder to break, you might not be the first that's being broken. I mean, if you're running in Africa, for instance, and there's a lion coming after you, you just have to run faster than the guy you're running with. So doing nothing makes you an easy target, makes you a sitting duck. And I don't think that's a very good strategy.
Thank you for that, Johannes. With that, I'm taking it over to questions that were asked in the channel. So here's the first one. Engineering for resiliency sounds like an industrial version of the chaos monkey approach by Netflix, so that continual process of whacking things and see how they break and then improving them over time. Do you envision this will become somewhat similar, the resilience approach that you were outlining in your talk?
I'd rather think that we'd be able to prevent that situation if we are able to think about security and resilience from the get-go. If we are able to build in the stuff that the defenders need in order to be able to defend a system, and to build in the stuff that you need in order to be able to update the system, then make the defender's life easier, and you're not going to be running around whacking a monkey.
Thank you for that. And yeah, I couldn't agree more. I had kind of a similar discussion, I think the other day with some colleagues, where it was about like, usually we learn from those huge accidents, right? I mean, it should not be the Sevezos and Bhopals and 3 Mile Islands and Fukushimas that force us as quote unquote the industry to move forward. And actually the example I was giving to that colleague was, so I have a pilot license, so I'm somewhat of a crazy aviator, flying hot air balloons. But the most important takeaway for me in aviation is exactly that whole culture around how to learn from mistakes, not pointing fingers at anyone at the get-go, but investigating why something happened and what can we do to avoid this exact thing from happening. So iteratively trying to get better, fully aware that we will not solve this 100%, but we can at least make this one thing go away by enhancing technology or process or whatever. So iterative approach, but not rebuilding from the ruins every time.
We have that Deming circle for a reason. Continuing improvement.
Exactly. Yeah, CIP used to be the other big term apart from non-functional requirements that I referred to earlier in the automotive industry. And yeah, again, I thank you for especially outlining that in the risk matrices, which should drive home the point that security goes along with safety and is not a non-functional requirement. It is actually ultimately a functional requirement.
As Tiff once said, can a safe system be secure when it can really be safe when it's not secure?
100%. Thank you so much, Johannes, for your insights here.